So in our last lesson, what we were talking about was the hydrogen spectrum and how that actually relates to what we have over here, which is the Bohr diagram of the atom. And I said, yeah, it works spectacularly well, but only for hydrogen, which is a little bit unfortunate. Now, in grade 11, you actually ended up using the Bohr diagrams all the time for doing your work. And largely that's because in grade 11 you focus on the first 20 elements on the periodic table. And the Bohr diagram works fantastic for that. It doesn't work so well for transition metals though, and understanding why they have their various charges and so on. Now, I said the problem comes out of the actual spectrum. So if I give hydrogen different amounts of energy, I get these different color bands showing up. If I do the same thing for neon, and this to the right, there's 1, 2, 3, 4, 5. In grade 11, you could have had up to 6 rings around the nucleus, saying, okay, that actually covers the pretty much the whole periodic table. But in terms of these jumps for the electrons to make from the second level to the first, from the third to the first, and so on, there's not enough gaps to explain all the different lines that show up in the neon spectrum. And this is true for everything that is not hydrogen. So the scientists had to come up with a better way to explain this. And really what they did, and this is a very simplified version, so you can go much more in detail with this. But what they found is actually there are more energy levels than what we're showing here on the Bohr diagram. And this is the new picture of the atom that we come up with. If you think down here, this is the nucleus. This is kind of like your first ring that you had in the old model. In the second ring, in the old model, you had a single ring. In this model, the second ring is actually made up of 2 separate energy levels, the 2s energy level and the 2p energy level. The third ring in the old system was, again, a single ring. Now it's made up of 3 separate energy levels. And I'm going to explain to you how this works out. There's a number of ways that you can look at this. We're going to look at one way to go about that. So, if you look at this periodic table, the first ring you could think of as being the hydrogen and the helium. Electrons from hydrogen and helium go in there. The second ring would have included lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So electrons from each of those atoms would fit in the first 2 rings of the Bohr diagram. Third ring would actually include sodium, magnesium, scandium, titanium, vanadium, chromium, all the way across here, and these guys as well. And this should start to make you feel a little bit uncomfortable, because why did we skip calcium and potassium? And there's reasons for that. But the old system, what we talked about is we talked about rings. The new way of describing the atom, or the quantum mechanical way of describing the atom, talks about 4 pieces of information to know where the electrons go. What we're really looking at is the location, or the address, or the energy of each electron in the atom. So the first piece of information, this is exactly just like the numbers from the old rings. So it's exactly like the way that worked out. And the way that these numbers work out, you have possible values. There is 1, 2, 3, 4, and you can just keep going on like that. Okay, this is how this works out. The greatest number of electrons that can be in any energy level is, we'll get into that a little bit later, how that works out, because you're going to learn how to figure this out actually yourself. Those numbers, 1, 2, and 3, that would correspond to the yellow being the 1, the orange being the second energy level. So N equals 2 is that orange color that we've got. That's N equals 2. N equals 3 is going to be the green color here. And so on. The second piece of information that you have to know is you have to know within the energy levels. So within a given, in the old system it was ring, now we're going to talk about the energy levels. There are energy sub-levels. So each, again, I keep referring to the old system, but each ring, so the first ring has only one sub-level. It's only itself. The second ring is actually broken up into 2 sub-levels. Okay, there's actually, like, you can kind of picture, it doesn't work, but you can kind of picture 2 separate rings that it's made up of. Third ring, it has even more. It has 3 sub-levels. In the quantum mechanical model, what we talk about is we talk about the second quantum number being the orbital shape number. So what that means, if we go back to our periodic table, the first energy level, so N equals 1, and again from highlighting, we're talking about the elements that are highlighted with yellow. Their valence electrons are in the first energy level, N equals 1. So for N equals 1, there's only one type of shape. It's a spherical shape, and we call that an s orbital. An s orbital. Its mathematical number is 0. The term we use is s. And we call this block of the periodic table over here, this is called the S block. Because what it means is that the outermost or the highest energy electrons in any of these elements, the highest energy electron will always be located in an s orbital. It's also easy to figure out how many electrons fit in an s orbital by counting how big the s block is. So I have 1, 2 elements as I'm going across it. There are 2 electrons that can fit in the s block or in an s orbital. This section over here, this is known as the p block. And in the p block are all of these elements. What that means is that each of these elements, their outermost electrons, is in a p-shaped orbital, or a p energy level orbital. So we have 1, 2, 3, 4, 5, 6 elements across the p block. And that means that there are 6 electrons that can fit in p orbitals of any energy level, of any principal quantum number. This middle section here of the periodic table is known as the D block. There's 10 elements across in the D block. That corresponds to the fact that there are 10 electrons that fit into d orbitals of any energy level. And so if I pick an element in here, I can pick molybdenum, Mo, and right away I know it's here. I know its outermost electron will be in a d orbital. Done. If I pick xenon, I know its outermost electron will be in a p orbital. At the bottom, and we won't use these very much, but at the bottom where you have all your actinides and lanthanides, this is known as the F block. There's 14 elements across. That means F orbitals can hold a maximum of 14 electrons at any energy level. That's how that works out. In terms of mathematical numbers, the L value for a p orbital is equal to 1. The L value for a d, or the second quantum number for a d block, is equal to 2. And an F orbital has an L value of 3. So let's look at how this works out. Keep going down here. So the second quantum number, and that's where I was talking about the S, the D, the F, the P, all of that stuff. Okay? It's called an orbital shaped quantum number. It tells you the energy and shape of the sublevel. Possible values for any energy level. So it's a formula. The possible values are 0, and we can start from n minus 1, n minus 2, keep going until you get to 0. So how that looks, if I've got n is equal to 3, the possible values in that third, remember n is like the ring, the possible values for the shape or the second quantum number are 2, that's n minus 1, or 3 minus 1 is 2. 1, that's n minus 2, or 3 minus 2. And 0. So we've got 0, 1, and 2, which means in principle number 3, I have S-shaped orbitals, I have P-shaped orbitals, and I have D-shaped orbitals. And just to show you what that looks like, I'm going to go down here a little bit. You should be able to recognize these. An S orbital is simply shaped like a sphere. That's all that it is. A p orbital, sometimes called a dumbbell orbital, it has this 2 lobes shape. Now the one thing you have to know, any singular orbital, so this orbital can hold 2 electrons max. This orbital, this is one shape. It's got 2 different lobes, but it's just one shape. This can hold 2 electrons. This can hold 2 electrons. And this can hold 2 electrons. And these come in sets. So this is an S orbital. This is a p orbital. So if I'm in energy level number 2, it has a p orbital. And the p orbitals come in a set. They come with a px, a py, and a pz. Oh, I got those backwards. It's a pz and a py in this particular image. pz, and py orbitals. Taken as a whole, they can hold 2, 4, 6 electrons. Go back to our periodic table. That's why in the p block, so second energy level, that's these guys. P block, it can hold 1, 2, 3, 4, 5, 6 electrons. It holds 6 electrons because 2 electrons in each of the p orbitals, and p orbitals come as a set of 3. So if you have one p orbital, if you have a p orbital, you have the set of 3 p orbitals. The next type of orbital, it kind of looks like a 4-leaf clover and then a dumbbell with a donut around it. This is all derived mathematically. Is 1, 2, 3, 4, 5 orbitals. Each of these can still hold 2 electrons max. So 2 electrons fit in the dyz, 2 electrons fit in the dxz, 2 electrons fit in the dxy, and so on. 2, 4, 6, 8, 10 electrons. The D block is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 atoms long. There we go, or 10 elements long. So the D orbitals can hold, at each energy level, can hold a maximum of 10 electrons. That gives us a bit of the shape of the electrons, or of the orbitals, I mean. And these shapes, what they are, the way they come up with these, is the electrons themselves, they can be located kind of anywhere in this region of space around the nucleus. The middle of this is the nucleus. The middle of the X, Y, Z is the nucleus. The way they come up with these shapes is really it's a probability shape. And so if you can see in this lobe, there's like a darker section in the middle and then a less dark on the outside. If you take millions of pictures of the electron where it's located at each instant of time, you get a bit of a picture that shows you, it kind of turns like this if you overlap or if you stack each of those photos one on top of the other. So more often it is in this region, less often it's on the outer edges of this, but it is a probability. You can't know, and this is something that's called Heisenberg's uncertainty principle, you can't know the location and the velocity of an electron to a perfectly precise amount. There's an entire lesson, if not an entire course, on why that is. It bothers a lot of people. So let's keep going here. The third quantum number is the orientation in space. So when I talked about the orbitals for the P, I said we've got a px, we've got a py, and we've got a pz orbital. If I want to say I know that the electron is in this orbital right here. It's not in the x or the z, it's in the py orbital. Oh, and I got the y and the z mixed up yet again. Let me change that. So it's in the pz orbital, sorry. The electron is in that pz orbital. That's derived on using what's called the magnetic, or the ML number. And we talked before that a p orbital, p or p, is given the mathematical number of 1. So L, the second quantum number, is equal to 1 for a p orbital. P orbitals are broken into the x, the z, and the y. And the way that we do that is with the magnetic quantum number, ML. And what that says is it is the negative L value to the positive L value. So ML is negative 1, comma 0, comma positive 1. And what that really tells me, this orbital can hold 2 electrons, this can hold 2, this can hold 2, which gives me a total of 6 electrons that fit into my p orbitals at any energy level. The values of ml, like it said, depends on the value of L, the second quantum number. And the way you do that, it's negative L to positive L and all the integers in between that. We've got one more quantum number, or one more way to identify a specific electron. And what that's called, that's the fourth quantum number. And the fourth quantum number is the magnetic spin. There's only two possible values, positive 1/2 and negative 1/2. Mathematically, two electrons in the atom can never have exactly the same address, or all the information about it can't be the same. So what that means is if I've got an electron in here, and positive 1/2, we sometimes call that spin up, and negative 1/2 being spin down, if this is representing to the two electrons. In this orbital, if I have one electron that is spinning up, the other one must be having a spin down value of that, the magnetic spin number. It's impossible to have two electrons in an orbital with the same spin. They can't both be spin down. They also can't both be spin up. They have to be opposite each other. One has to be spin up, one has to be spin down. This is a massive amount of information that we've gone through, and we're talking many, many years of scientific research. So let's bring that down to something that's a little bit more palatable with a couple of sample problems. It says this: what values of L is the shape number, or the second quantum number, and ML is the magnetic, or the orientation in space. I always think of L as shape of the orbital, and ML is orientation of the orbital, not the electron. So what are the values allowed for a principal quantum number of 2? Well, let's look at that. If n equals 2, I have my L values, and the L values that I have are 0, and I keep going up until I get to n minus 1. So 0 and 1. Those are my possible L values. 0 is a s orbital. 1 is a p-shaped orbital. So S is the spherical ones, P is the dumbbell-shaped ones. The ML values for each of these. For an s orbital, I go from negative L to positive L for the ML value. Negative 0 to positive 0, simply 0. For 1, it is negative 1, 0, positive 1. Each of these, this is an orbital. This is an orbital. This is an orbital. And this is an orbital. So that tells me that I have 1, 2, 3, 4 separate orbitals for n equals 2. And this is going to take you back a little bit, but if you remember, n being 2, that's like the second ring. How many electrons did the second ring hold? Well, in grade 11, the second ring could hold a maximum of 8 electrons. Hey, look at this. 4 orbitals, each one holding 2 electrons. That means there's 8 electrons that can fit in that one, in the second ring. The other thing that you did in grade 11, if I had my diagram, when you drew it, you drew it like this, and then you doubled up electrons for some reason. The reason why is each of these pairs of electrons are fitting in an orbital. So this pair might be this orbital, this one might be this one, and so on. We'll take one more as an example. It says here, what are the possible values for ML if n equals 5 and L equals 2? So I've got my principal quantum number equal to 5. The L values for that are 0, 1, 2, 3, and 4. Those are all the ones that exist. We could look at them all, but we're only focusing on this one. What are the possible ML values? ML. And the ML values that I've got for 2 would be -2, -1, 0, 1, and 2. Those are my 5 possible values that I can have. 2, in terms of what type of an orbital is associated with this, this is a d orbital. In terms of our letters, 0 is an S, 1 is a P, 2 is a D, 3 is an F. We don't even have to worry about 4. It exists, but we don't use it. Final question we'll take a look at on this section right now is, what is the set of quantum numbers for one electron in the 4s orbital? So n is equal to, the number in the front is always your n value, 4. L equals s orbital, that is got a value of 0. ML, it's always got to be -L to positive L. There's only one option, has to be 0. And MS, an electron can either be spinning up, or it could have a -1/2 or a downward spin and still be in the 4s orbital. But those are the only two possibilities.